Hello, and welcome to the next section on equilibrium. We're going to talk a little bit in this section about reaction rates. And I know we've already discussed different factors that affect the reaction rates, but what if we mix all of our reactants together in our beaker and nothing happens? And we wait and wait and wait and wait, and nothing ever happens. Actually, there are many conditions that need to be met in order to produce a chemical reaction between molecules. One thing you can think about, a question to ask, what if all collisions between molecules resulted in a chemical reaction? How would life be different? It would be very different. There are many collisions that happen and they do not produce chemical reactions. Why is that? What is going on? Well, there's something that we need to talk about, and I'm sure you've heard this word before, activation energy. Activation energy is the minimum amount of energy needed for the reaction to occur. When those molecules bump into each other, if there is not enough energy to break bonds and allow other bonds to be formed, then there will not be a chemical reaction. So, if the collision energy is less than the activation energy, the molecules just bounce apart unchanged, bump into each other and bump into someone else, bump into another molecule, bump into the side of the beaker, but they don't change. There is no chemical reaction that occurs. Here's just an example of that. Here we have our reactants. If we have activation energy that is greater than the collision energy, we don't get a product. The reactants will just sit there. So probably you're already thinking in your mind, oh, I know how we could make this happen. If our activation energy is greater than our collision energy, then we just need to add more energy, right? Right. Well, how could we do that? We could raise the temperature, right? Increase the temperature. We will have then higher speeds of the molecules, more high energy collisions, more collisions that break bonds, and we will have faster reactions or simply have reactions. What if we increase the concentration of the reactants? We can do that. If we have more molecules per volume, we can have more collisions and more reaction events. So those are some ways that we can overcome the activation energy barrier. Are there any other ways you can think of? Can we speed up the reaction without raising the temperature or increasing the reactant concentrations? What do you think? Well, this is where we're going to talk about a very special molecule called a catalyst. Catalysts are really important. They speed up a reaction without being consumed. A catalyst is a molecule that can come in, speed the reaction up, and then leave the reaction and be used again and again and again in the reaction over and over with different molecules. How does it speed up the reaction? Well, it does that by lowering the activation energy. So when we add a catalyst, instead of our activation energy being way up here, it lowers the activation energy to be right here. So these reactants can combine at a lower energy to produce the products. A lot of different examples of catalysts. Chlorine atoms are one example of catalysts. They catalyze the decomposition of ozone. And if you'll remember from other science classes, ozone is an important component of our atmosphere. It absorbs UV radiation from the sun and protects all of us from, and all of life on Earth from being damaged by the damaging UV rays. And chlorine, when we have a chlorine atom, it catalyzes the decomposition of ozone. Here we see it being used to form chlorate ion and oxygen, which then goes back to form a chlorine atom and oxygen. So in the end, Chlorine this is sort of the intermediate step, if you want to think of it that way. Chlorine is a catalyst because it begins by reacting with the ozone, the O3, and the product that is formed is O2 and the chlorine atom again. So it can go on and catalyze another reaction of the decomposition of ozone. Another example of a catalyst would be in a catalytic converter in your automobile. Palladium or platinum, either one can be used as the catalyst. They basically catalyze uncombusted hydrocarbons, the reaction of taking those and forming carbon dioxide and water. They are the catalysts in those reactions. What are enzymes? And these are really important. Enzymes are catalysts. They are very special catalysts. They are biological catalysts, and they're very highly selective. An example, here's just one of a lot of different examples of enzymes. Carbonic anhydrase catalyzes the reaction of carbon dioxide and water, forming carbonic acid. So here are different classes of enzymes. You definitely don't need to memorize these. It's just interesting to read what some of them do. There are many, 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 many different enzymes that belong to each of these classes, but these are just a few of them. And they do really important things like breaking lipid molecules down, converting glucose into fructose, and on and on. You can just read some of these. It's very interesting. Organisms could not live without enzymes. They're very important catalysts in biological systems. One more thing to note before I end this section, and that is the graphs that I was showing earlier all showed reactants having a higher energy than the products. But it doesn't necessarily, that is not always the case. We can have reactants that are at a lower energy than the products. The products can contain a higher energy than the reactants. And in that case, you can still need to have a catalyst. There can still be an activation energy, and the graph would simply look like this. So advanced ideas. Here's some great questions. Look, how about the ozone layer? What geographical areas do we find the greatest ozone depletion? What is the effect of that on plant and animal life? Is the hole in the ozone layer continuing to grow? And what products contribute to this problem? Great questions to ask. Look into some of these things. Research different biological enzymes. If you're interested in looking at biological catalysts, look at enzymes, their functions. Why are they so important? What do they do? Look at exothermic and endothermic reactions. And we've mentioned that at different times, but look at heat and energy. What would the energy versus reaction path graph look like for each of these types of reactions? How would that be different in chemical reactions? So I look forward to seeing what you have to show me, and I'll see you in class.